So we're going to look at determinants and inverses, but start off with, again, a determinant. And what am I going to say? A determinant is a single number. Okay, it's a single number. Let me show you how to find that determinant, and then we'll also find an inverse. You're going to walk away today realizing that most of this involves some formulas. Okay, they don't have to be scary, but they are going to be some formulas. Let's see how it works with a determinant. First off, we need like a generic 2x2 matrix. Make sure you understand what I'm showing you here. There's some 2x2 matrix. We're going to call it matrix A, and it's filled with 4 numbers, A, B, C, D. You'll probably want to jot that down because we will use that for the whole period. We'll use this generic A, B, C, D for the whole period. Again, there's some matrix A. It's a 2x2, so it's got 4 nums in it. We're just going to call them A, B, C, D. So, what's the determinant? Well, it's a formula. And it's a formula that says that all you got to do is multiply the diagonals. Okay, now the diagonal would be like A times D. A times D. So I multiply, and that's why you see AD. The other diagonal would be B times C. So I multiply, and that's why you see BC. So you multiply the diagonals and subtract. Now there's a little bit of notation up here. If you're writing the whole thing down, that's good. Make sure you know what you're writing down. First of all, we abbreviate the word determinant. We like to do stuff like that because it keeps it simple. So when you see the abbreviation DET, that stands for determinant, maybe you notice that the matrix looks a little different here. It doesn't have like the little brackets around the lines. It doesn't have the brackets. It's just like straight lines. When you see straight lines like that, that's not a typo. That also means determinant. Okay, I'll show you, but basically you want to follow the formula, which says to multiply the diagonals and subtract. By the way, you have to multiply in the order that is shown here. In other words, you have to do the main diagonal first. The main diagonal is the one that I'm showing here, and then you subtract what we call the secondary diagonal. So, let's see if you can find the determinant of this nice little 2x2 matrix. And as you're writing this down, make sure that you notice, like this important, make sure you notice that there's like these straight lines around these numbers. As soon as you see straight lines, that means do the determinant. Okay, so I've got 7, 9, 3, negative 8 with the straight lines saying, hey, do the determinant. So I'm going to take the, as we call it, the main or primary diagonal. So the main or primary diagonal has 7 and negative 8. Of course, you're going to multiply those. That's why we're going to write down negative 56. And then you do the secondary diagonal. The secondary diagonal has 9 and 3. So you multiply those, and that's why we're going to write down 27. Now, you always subtract when you do a determinant. It's just the way it is. We didn't really talk about so much why. And you get negative 83. That number probably doesn't mean much to you right now. That's okay. It doesn't need to mean too much, except that that is the determinant of those 4 numbers. Don't worry, it will mean something soon. Right now, we're just trying to work it out. What if you would see something like this? Like we did yesterday, we start to insert some x's. So we see x, negative 3, x, and 4, and it equals 28. Okay, now there'd be some things you'd want to notice. Once again, those straight lines. I'm trying to emphasize that because sometimes people don't notice them, but you just see straight lines. That means determinant. Oh, and we're already telling you what it equals. We're telling you that it equals 28. That's nice. I gave you the answer, but I gave you the answer so you can solve for x. Now, the hope is that anytime you see a variable, that you do the same thing. So follow the little formula. You multiply. So how you doing multiplying x times 4? It's just 4x. Okay, we're going to multiply the other diagonal. Again, how's that going? -3 times x. Now, according to the rule, and be careful about this, you always subtract. So in a problem like this, we want to kind of feel like there's two subtraction signs, but you always subtract according to the rule. And that's supposed to equal 28 just because that's how he gave it to you. Well, that's not bad. It's just a little equation. Okay, I know you guys know how to solve that. We're going to get a little plus plus. We're going to get a little 7x. Tomorrow/Friday, you guys are going to get an assignment full of all kinds of these goodies with x's and such. So just kind of warming up a little bit. This is how you do the determinant of a 2 by 2. How about if it's bigger than a 2 by 2? How about if it's greater than 2 by 2? This should say greater than, not equal to. Okay, so if it's greater than a 2 by 2, then we have to use more of a technique. It's called expansion by minors. Okay, now what I'm about to show you here, sometimes the first time you see it, it's a little bit of like, what? But give yourself a chance. It's actually a method. I don't have a formula I'm going to flash up here. So if we have something that's like a 3 by 3, we're going to have to expand it. Let me show you. We're going to actually do it with some numbers. Here I'm using the abbreviation. So if I use the abbreviation, then I can go back to the regular matrix brackets. But we're going to fill this thing up with 9 numbers. So 893, 357, and -124. Now, just as the little technique says, we're going to expand this. Expand, of course, means it's going to get a little bigger. We're going to expand it into minor matrices. Minor matrices, which will actually be smaller. So there's kind of like this expand, get bigger, into stuff that's smaller. Okay, let me show you. We're going to expand across the first row. What does that mean? Well, it means that each number that's in the first row is going to become a coefficient. And each number is going to get covered up according to the column and the row that that number is in. So again, I see the number 8. It's like the first number we get to. I'm going to use it as a coefficient. I'm also going to cover up its row and column. And what do you see? It's supposed to be pretty clear that we have a smaller matrix. It's called a minor matrix. We have 5, 7, 2, and 4. Okay, again, just kind of observe, give this a chance. You don't have to have it all figured out the first time, but I'm going to go to the next number, which is 9, okay, because I'm expanding across the first row. Now I'm going to cover up the row and column that contains the number 9, and we have another minor matrix. You should see a 3, 7, -1, 4. Now, remember that 9 is going to be like a coefficient, so you see me writing it down, but we're definitely going to write down 3, 7, -1, and 4 as a minor matrix. Maybe you want to try to do it for the last number. It would be the number 3. Promise it's going to be the same thing that we've done, even if you're not sure where this is headed. Okay, so you should have wrote down a 3, and then a 3, 5, -1, 2. Now, I would suspect that you have some questions about where this is going, but do you have any questions just about what I've done so far, basically covering up numbers and writing down the smaller 2x2s? Are you sure you're okay with that? Let me give you the next piece of the puzzle. These three things get attached. Right now, they're just kind of like floating out there. They get attached with a little pattern. The pattern is, the first one's a plus, the second one is a minus, and can you guess what the third one's going to be? Well, it's a plus. I'm not sure you would know for sure, but it goes plus, minus, plus. Okay? Now we kind of feel like these things are connected. Now be careful. Don't do this. Don't do this. Don't distribute. You might say, well, that's what you did yesterday. Yesterday, that was a matrix. This is not a matrix. This is a determinant. That means that we can calculate it. So this is very important that you realize that all three of these 2x2s can be calculated. I'm talking about this. It's called the determinant. So you can go through each one of these and you can do 20 minus 14. 20 minus 14. Now, maybe you just want to write down the result, but some of you, if it's helpful, you can write down 20 minus 14. I'm going to just write the result to kind of keep it simple. Be careful on this one. It's 12 minus negative 7. 12 minus negative 7. Okay, I wrote that up above so that we can clearly get 19. And maybe you want to think about the last one if you haven't yet. Okay, so the last one would be 6 minus negative 5. I hope you feel like that at this point we basically have a little multiply, a little add, subtract, basically some order of operations. So, multiply these and get 48. Multiply these and get, I'm going to take a peek and get 171. Multiply these and get 33. But whatever you need to do, at this point, you could pop this all in a calculator. Just understand that you're basically adding and subtracting. And you end up with a number. You end up with the determinant. Okay, it equals negative 90. Negative 90. Okay, if it crossed your mind at all that sort of like, what is this, Miss Nail? You're just making this stuff up as you go. Trust me, I'm not. Okay, but I realize it kind of looks like it's sort of random. Here's some interesting information. I didn't have to expand the first row, although most kids do. I could have expanded the second or third row. Okay, depending on which row you expand, you have to use a certain pattern. I'll tell you what, I'm just going to put it up here. Now, the pattern that we used was plus, minus, plus, which most people are going to do for most problems. But if you did the second row, it would have been minus, plus, minus. Okay. Oh, so the third row, take a guess. Plus, minus, plus. So you can actually pick any row that you want. Even though we don't have time, the interesting thing is that you would end up with the same answer. And that is kind of amazing. If we had done any other row, we still would have gotten negative 90. Try one. Try one. It's kind of fun in a strange way to manage this method and see if you can end up with that one single number. I got 460, 2 negative 15, negative 361. Most of you are going to expand the first row. I just have a feeling, which is a good idea. If you're a little more daring and you just want to try something different, maybe you want to try the second row. or the third row. Okay, but try it. I'm going to do the first row if you want to be able to compare the exact same numbers. If at any time you want to just take a glance up here, I know it's a lot of numbers to look at. Maybe you just want to focus on your paper and see if it comes out the same, but you're welcome to look up here and compare. I also have given somewhat of a subtle hint for the last minor matrix. I'm not really trying to be funny here, but I'm giving a true hint about how you can use the number 0 to make your life a little easier. The answer comes out to a 3-digit negative number in the 200s, in the negative 200s. If when you hit enter, when you're all done and you have a negative 200 something, that might be good. So we have a 4, we have a negative 31, we have a minus 6, and a 17, and that's it. Okay, when you have a 0 that's part of your row, it makes your calculations simpler. Okay, when you have a 0 that's part of your row, it's automatically going to equal 0 anyway. So these 4 numbers, when put together, give you negative 226. I promise these numbers will mean something. You just have to come back, okay? But it's called the determinant right now. What do you think? Anything we can say? Was anybody daring and used like another row? Okay. Sometimes there'd be somebody, you would still get negative 226, which is kind of cool. Kind of cool. Now, maybe you remember on that first slide that we had 2 things we were going to talk about, a determinant and then something called an inverse. Something called an inverse. As a little segue, I want to show you 2 matrices. You probably can just watch this. You don't need to get too bogged down with copying it down. Probably just watch. But I want you to look at these 2 yellow matrices. And let's multiply them. We're going to do it kind of quickly, but I think for most of us, you can just kind of think with me a little bit about multiplying. It doesn't hurt to remember that it's a row times a column. And that's going to be 1 times 4 and negative 3 times 1. So that's like 4 and negative 3. Now remember, you add when you multiply. So it's 4 plus negative 3. So that comes out to be 1. What's next? Row times the next column. How you doing? You should be seeing 6 and negative 6. 6 and negative 6, when they add, are 0. There's something special happening here. Maybe you're not sure what, but hang in there. Because if you multiply the next one, now this is negative a half times 4. That's negative 2. And then 2 times 1 is positive 2. 0 again. 0. And then the last one, negative a half times 6 is negative 3. And then 2 and 2 is 4. I know it's a lot of numbers, but negative 3 and 4 come out to be 1 again. This matrix in green, it's a special matrix. You might notice that it has 1s in the diagonal and 0s everywhere else. That's how I want you to see it. It's got 1s in the diagonal and it's got 0s everywhere else. We call that matrix the identity matrix. Now, some people will write down the identity matrix if you want to. I'm just being honest with you. For most of us, it's something you can just kind of listen to. What is the identity matrix, though? It's a matrix that kind of behaves like the number 1, which means that if I would multiply something times the identity matrix, it would come out the same. And that's because these two yellow matrices are inverses. Okay, now I just kind of want you to see that when you have two matrices that are called inverses, they do something special. They turn into the identity. What I'm going to do is show you guys how to get an inverse. Go ahead.
Is this still considered the identity matrix if the 0s and 1s switch places?
It is not. It has to be such that the 1s are in the main diagonal. And I think there'll be a problem we do someday where you'll see, oh my gosh, if you have 1s in that diagonal, that allows you to multiply and get the same thing. I might show you something like that tomorrow. The main thing I want you to hear is that these two matrices are inverses because they multiplied to be the identity. And in mathematics, inverses always get you an identity. So let's talk about an inverse. Okay, you've heard the word inverse before. We talked about it in the last chapter. Now we're going to do a matrix inverse. I'm back to my ABCD matrix. Do you still have it written down? To do the inverse, it's a little formula. Now this one looks kind of like an alphabet soup and a mixture of A's and B's and C's, but take a careful look. Take a careful look. There's some stuff that's happening with A, B, C, and D. First, you get this like fraction. Now, I know this might not be the most exciting thing ever, but it's new, and you guys will find that we will do stuff with this. But for now, just notice there's a fraction. It's 1 over AD minus BC. It tends to be that that's the hardest part for kids. They miss that it's a fraction. They forget that what this AD minus BC is. AD minus BC. Oh, that's the determinant. So it's going to be like 1 over the determinant. Okay, so there'll be a fraction. Over here, we have like a switcheroo. I hope that you kind of feel like that the diagonal A and D switched position. Now the diagonal is D and A. The other numbers, B and C, just became the opposites. So that's why we have the opposite of C and the opposite of B. So there's like this switcheroo that occurs. There was a year where a student drew this little diagram. It was pretty crafty. And actually, it seems to be a nice way to remember this formula. 1 over the determinant. Do you see what's going on with the diagram? Switch these numbers. Make these numbers the opposite. If you like this diagram, the student didn't have any royalties on it, so use it. Use it to help you get an inverse. Make sure you get comfortable with the notation. I'm giving you a matrix. A lot of times we'll call it A or B. We could call it anything we want, but matrix A is the numbers 4, 6, 1, 2. Okay, that's nice. Let's find the inverse. And I hope you see the notation with that little a to the -1 that stands for inverse. Now, to find the inverse, you're going to need to kind of do two things. You're going to need to find a determinant so that you can put it in a fraction, and then you're going to have to do the switcheroo. Make sure you realize you have to do both of these. Let's do the determinant. Hopefully you're getting a little bit better at these. That's just the old diagonal minus diagonal. Okay, 8 minus 6, if you want to see it written out, and comes out to be 2. Whenever you do a determinant, you always subtract the diagonals. Now, as I get closer to getting this inverse worked out, what I'm going to do now is I'm going to use this determinant so that I can write it as 1 over 2. And again, that's the part that people seem to forget. It's always 1 over, so it's 1 over 2 that I found. And then there's going to be this switcheroo. Okay, now the switcheroo can be pretty simple. Don't overthink it. You just take the numbers 4 and 2 and you switch their position. That's why it's now 2 and 4. The other numbers become the opposite, and that's why it's a -6 and a -1. I know usually what the problem is, and it's really this next step. It's not hard, but it's understanding that this needs to be put together. How do you put it together? Well, by doing what it says, by multiplying 1/2. Now, you got to understand we're going to multiply 1/2 because this is scalar multiplication into this matrix. Basically, we're going to simplify it to be one final answer. Okay, so yeah, just cut everything in half. Nice and easy with that kind of fraction. And we end up with these new numbers. That is the inverse. Now, I told you not to copy something a few slides ago, but I am kind of curious, by chance, do you recognize these numbers? Maybe you don't, but let me remind you that they really were our two matrices. I kind of wanted to show you that you can either find the other matrix or you can multiply them together and you can see that they equal the identity. But either way, there's kind of no denying it that these two matrices are inverses of each other. Try a new one. Try one that we don't, so to speak, know the answer. So here's A. I have to give you A, 3, 2, 5, 3, and see if you can find A inverse. Remember, there's like two parts to this rule. You get a fraction out front, and then you do a little switcheroo. Now, the number that you get out front, you might say, Mr. Nair, it's not really a fraction this time. No, it's not. It's just 1 over -1. So the number out front is really just -1. Can you multiply that to the inside? What did it say?
What was the last word of this?
Oh, always create an identity. So the number outside is from the determinant. Actually, let's kind of start here. It's the determinant. That's that diagonal subtraction diagonal. So we take 9 and 10. Subtract those. So 1 over negative 1. It's always 1 over the number outside. 1 over negative 1. Maybe you didn't feel like the 3's really switched. Well, just pretend that they did, but the other numbers become the opposite. And now, here's the part that, again, kids seem to have trouble with, but seriously, this is just 1 over negative 1. That's like negative 1. I'm going to multiply negative 1 to all 4 numbers. Going to feel like there's like a switchback again. If you multiply negative 1 to all 4 numbers, now we end up with negative 3, 2, 5, and negative 3. Okay, that's called the inverse. Okay, these two matrices are special. I'm not going to do it, but we can kind of mentally say, if you would multiply them, and sometimes you just can do the first one and you can start to see that 3 times negative 3 is negative 9, 2 times 5 is 10. We're back to getting the 1, 0, 0, 1 matrix. It's going to work. Okay, it always does. I'm looking at the clock and I'm looking at this problem and I'm saying, if I show you this, it's going to be short, but it'll benefit us next time. So let me kind of somewhat squeeze in this last one, but there's a reason it's going to be short. Okay, here's one more matrix, 4, 2, 6, 3. 4, 2, 6, 3. And one more time, we're going to find the inverse. Well, you'll see. We're going to find the inverse. Wink, wink. What do you notice here? Are you running the rule? It's 1 over 0. You should be getting 12 minus 12. 1 over 0. 1 over 0. Hey Siri, what's 1 over 0? Well, it's not good, right? Listen, what we end up with here is a no can do. In other words, the inverse does not exist. I'm not even going to bother doing anything else, because the inverse does not exist if the determinant is equal to 0. That's a nice little closing statement there. The inverse does not exist if the determinant is equal to 0. So put that in the information packet for today.